Okay, so we're going to talk about symmetric spaces. So if you want to,
compact ones, is that right?
that's what I'm interested in. Yeah.
Okay.
So I don't know if you want to remind us of this diamond cutting idea. And well, first, another thing I could do is just like yank up the some list of the classification of symmetric spaces, just so we know what the 10
Let's not do that yet. Let's think of that as the back of the book that we don't want to quite yet look at.
Okay.
So maybe I will just try to say some very amateur things about the diamond cutting idea. We're not sure if this is really the right tool. We don't know if what we're dealing with here is actually a diamond, but we're going to try to apply the diamond cutting idea to it. And the diamond cutting idea is an idea that you wrote about in this week's Finds 193. Now, I'm not sure that you didn't write about it somewhere else, because when you're in 193, you're talking a lot about E8.
Yeah.
And I don't know if there's some exceptional symmetric space associated to E8 or something like that. And I don't think we've just had a whisper about any ideas that, you know, your 10-fold way might secretly be an 11-fold way if you get some sort of division algebras from the Octonians or something like that.
I've been trying to avoid.
Yeah, let's try to avoid.
I will just mention that the 10-fold way is connected to the classification of division superalgebras, but those are associative division superalgebras.
Right.
And Todd Trimble wrote a nice article going through that classification.
When was that?
What?
When was that? Long time ago? Recently?
Sort of a long time ago. Yeah.
Okay.
It's on my website under the Todd Trimble stuff. And
I've been saying division algebras often when I mean division superalgebras, and John Werder says that's actually the professional way to talk. But,
okay. I'm not that professional, but
okay.
So, but anyway, I just wanted to it's supposed to be a super short digression, and it's already
sorry. It never is with me. Yeah, go ahead.
But because Todd was able to do that, I asked him to classify the possibly non-associative, but alternative division superalgebras. And at the time, I thought that was like a hard thing to do, but he quickly polished it off because the technique that works in the associative case works for them too. So anyway, there are these things that I've never heard anyone do anything with. Okay. But nonetheless, I just want to sweep all that up. Talk about it.
Sure. Okay, so I'm still trying to say something about the diamond cutting idea here. So this is discussed in week 193. So roughly speaking, the diamond is the sort of vaguely crystallographic lattice picture of the root lattice of a compact Lie group or something like that. And let's see. So, okay, maybe I'll try sharing screen and draw some amateurish pictures here. Okay, so maybe I can just try to draw a very sketchy picture of a root lattice here or something like that. So there's like A2 or something like that. And there's something very hexagonal about this picture. Like maybe that's my origin, and there's like a hexagon here or something like that. And maybe we're just supposed to pretend we understand what this means at the moment or something like that. But they're like these parabolic subalgebras that are like half of the Lie algebra or something like that. So like that over there. And I'm trying to remember how it works. This remainder over here has something to do with like the tangent space of the corresponding homogeneous space.
Right. So it's two-dimensional, for example.
Yeah, but it doesn't always evenly lie in just these 3 grades. In this special case, everything is just in 3 grades. You know, there's the middle grade, and then there are these 2 opposite grades.
Mm-hmm.
And, you know, there's all sorts of terminology that I should be able to remember, but of course don't, you know, beyond just parabolic subalgebras and parabolic subgroups and stuff like that. You know, there's like nilpotent. This thing over here is a little nilpotent subalgebra. What?
There are levies.
Levies. That was one of the buzz names I was trying to remember.
If you're sticking with a compact case, I guess your parabolics intersected with a compact gives you a levy.
Yeah, but all those things are secretly there.
Yeah.
But the diamond cutting idea is that, you know, think before you cut. You know, don't just start taking parallel slices of your gem, but hold it in your hand, or mentally hold it in your hand, mentally rotate it around, and find a grain or something. What's the word I'm looking for? What would be the diamond cutter's word that I can't think of? You find the right plane along which to tap the hammer so that it will cleanly fall into just 3 pieces. There's fun things that happens if it falls into 5 pieces or 7 pieces or something like that. But the first special thing that happens is that it cleanly falls into 3 pieces. And I think what that means is that the tangent space is an irreducible representation of the stabilizer of the homogeneous space or something like that. And that means that it's sort of a multiply homogeneous space. So it's actually a symmetric space instead of merely a homogeneous space. Except maybe I'm overstating the case. Is that going to be enough to really make it a symmetric space? I don't know. In week 193, you say something about Jordan algebras when you get this threefold falling apart into 3 pieces.
What did you say about irreducible?
Yeah. If, you know, we've got, this is like, what am I trying to say? Maybe this is like the compact Lie algebra or something like that. The compact subalgebra it's like the compact part or something of the, like you were saying, it's probably the intersection of the maximal compact and the parabolic or something like that. And when you want to, what's that called? You know, the restricted decomposition of, you know, it's like a branching rule or something like that. You know, when you're, you know, I mean, right, originally, like these weight diagrams are, you know, weight diagrams of irreducible representations of the whole big Lie algebra. But when you restrict to a sub-Lie algebra, like this single slice here, then the branching rule is kind of that, you know, this is an irreducible component, this is an irreducible component, and this is an irreducible component. It's just, that's the way it works. And this whole thing was the whole tangent space for the homogeneous space, for the parabolic homogeneous space, for the partial flag variety. And so if you know, if we didn't have any dots over here, then that means this whole thing is an irreducible representation of this subalgebra.
Yep.
And so, you know, so it's acting like transitively or something on the tangent space or something like that. You know what I mean? It's acting like so homogeneously on the tangent space that we're going to hopefully get a symmetric space out of this instead of just a homogeneous space. Is any of this making sense?
I hadn't known about that irreducibility criterion. Sounds like irreducibility is
in this diamond cutting context. I thought we kind of talked about it, but I don't know. Go ahead. Yeah,
it's possible. So
yeah,
the thing about symmetric spaces, as you know, is that you've got a Z mod 2 action on a Lie algebra, or a Z mod 2 grading on a Lie algebra.
Yeah, that must have something to do with this.
So it makes it sound like you're like gonna switch. It seems like something about reflection along this hyperplane or this line in this case.
So yeah, right. Let's try to invent something like that. Let's try to say that we're going to have this involution where this middle slice is the one eigen, the fixed things. And
it doesn't quite work out, right? Yeah, it doesn't.
No, I think it does. I think it does.
Well, okay, but the reflection doesn't act as -1 on those other.
No, but it flips those two things.
Yep.
And then the skew symmetric combinations of those or whatever are the the complexify, when you complexify or something, you get these things that are, I'm not saying this the right way, but
well, we could, this might, why don't we just, yeah, so why don't we try doing this example and seeing what happens?
All right, so this is, don't tell me, so this is SU2.
No.
SU3, thank you.
You're out of
SU3, okay.
Yeah.
SU3.
Because it's two-dimensional.
The eightfold way type thing.
And that thing that you've multiply outlined is for SU2, that slice.
Yeah.
Or
I mean, yeah, this
or SL2, depending on what you want to.
You're certainly suggesting the responsible way to proceed. I'll try to understand this a little bit before trying to just grab some of these diamonds and start slicing them up.
They're cheap.
We're going to practice on some diamond here.
Yeah.
Well, yeah, I mean, right, we certainly want to.
Yeah, I wonder if they're diamond cutting schools.
Right. Well, I think I got to practice on something. Right, you've already sort of forced me to look at this example, and as I think about this example, it doesn't seem that familiar to me, or maybe it is secretly familiar to me, but I haven't thought about it in a while. It would take me a while to recognize it. But that's encouraging me to try to take this very irresponsible attitude of let's just think about this diagrammatic diamond cutting task. We've got all these 4 infinite series of Dinkin diagrams for the 4 infinite series of compact Lie groups. And if we could figure out how to supplement those pictures, and again, this is the one for A2, which is SU3 or something like that. If we could, classify all the good ways of cutting these diamonds, then is that going to be enough to give us 10 different infinite families? I'm kind of suspicious because I'm not sure I could think of 10 ways of doing this. I mean, I have a feeling the thing we're doing to A2 here, I have a feeling that's going to work for any A series. But that seems like just one way of handling an A series. And then there's the B series. Yeah.
I mean, I just know, yeah, sorry, I'm trying to proceed without any knowledge ahead of time.
Yes.
So I just am cursed by knowing that there are these 10 series and that they do have nice descriptions in terms of the classical Lie group
diagrams, yes.
Yeah, I'll give you one other hint or something, which is actually going to make it sound harder. So I feel it's okay.
I just want to make it clear that I'm not, I'm so confused about this that I'm not sure whether I'm, making some horrible mistake somewhere. But keep going.
Yeah, I mean, I'm not sure that this is the right method to extract those symmetric spaces, but this seems like a pretty good method to extract homogeneous spaces of Lie groups, and the symmetric spaces are just some of those. They're some of the very nicest homogeneous spaces. So
the conjecture is that they're precisely the ones that fall into 3 pieces like that make the picture fall into 3 pieces.
Yeah, so maybe
maybe an over-optimistic conjecture, but go ahead.
Right. But I'll just say one other thing, which is that in the description of these symmetric spaces, they're very often described in terms of SU, SO, and SP. And the reason why I'm mentioning that is that they don't even like distinguish the SO evens and the SO odds in one of those constructions. So there's like some way to do them where you think more like more classically than thinking grammatically.
Sure.
So what I'm saying is that in some sense, I'm making your job harder because I sort of have this suspicion that like the BNs and the DNs,
those are the ones that are both SOs. Okay, yeah.
Yeah, are getting counted as just like one family here.
Sure.
But anyway, what my main point is that I think it's going to work. That is, I think there's going to be some nice.
Well, so let me try to go with that. So you're saying that there's like SUs and there's SOs and there's SPs, which stand for those sort of quaternionic things. And it sounds like you're telling me that I need, 3 numbers here adding up to 10. What do you think those 3 numbers are going to be? Or do you don't think it's going to work that way?
No. They typically involve 2 of those guys. Like you might have an SO included you might have a quotient of an SU by an SO.
Oh, well, now you're already making it sound just like what you've been telling me about. You're so, you're incapable of not, you know a lot of secrets and you're incapable of not giving them away. So yes, but there's of those 2, I'm hoping that one of them is always the ambient one. And that's what I was trying to get at.
Well, am I not supposed to say anything now? No, they take turns. Who's the ambient one and who's the non?
Well, that's what I'm saying. One of them is always supposed to be the ambient.
Oh, okay. I thought it meant always the same one.
I mean, now you're making it sound like you've got.
One of them is the ambient one, and one's a subgroup. Yeah.
Now you're making it sound like you've got a tic-tac-toe thing here.
Right? Yeah, right. Then it's a lot easier to imagine how you might get up to 10, although it's annoyingly.
But this is just reminding me of you were saying you were giving these homogeneous spaces corresponding to loop spaces or something like that, and it's always this thing modulo this thing, this thing modulo this thing.
Right. Yeah. Exactly. Yep.
So it sounds like.
I mean.
So is there literally going to be, one in each of these boxes except for one of the 9? No. No. One of them is going to have 2 of them. Maybe the one in the middle. No. Is one of them going to be doubled up or something like that? Or
you're making me want to show you the list of them. No, I know I do know, but it's sort of like you're trying to
Yeah, I'm trying to force it into a different mold here. But so it sounds like you're saying that. Yeah, I mean, right. So this one that we're doing here sounds like it's this one up here. That's what you're telling me.
That's right. Yeah.
Well, it's something. Yeah, I think that's what you're telling me. Because we've got like an SU2 inside of an SU3.
So what's SU3 mod SU2?
Say that again. What's what?
What's SU3 mod SU2?
Sorry, there is something bothering me here, which is that the SUs. I was worried that the SUs are so bland that they might not have any of the others inside of them unless you disturb the lattice structure in some way, don't respect the lattice structure in some way. But that might not be true. We might even stand a chance of actually, if you look at the gem in a funny enough odd angle, you might actually be able to find. I can't prove that we can't find some of those. So, okay, so I was interrupting you. What were you going to say again?
I was just going to ask you, what's SU3 mod SU2?
Okay, let me think. Don't tell me. All right. So okay. So don't tell me. So I guess there's just some general principle here that. What am I trying to say? That I always think of these things, these partial flag varieties, as holomorphic manifolds with this holomorphic symmetry. But part of the magic is that they're actually transitive, they're homogeneous under this compact subgroup as well. Right, so I can think of it. I should be able to think of this flag variety as just the projective plane.
Yep.
Wait, let me see if I can remember how the magic works. So the point is that they are complex homogeneous spaces. Yeah, I'm not saying exactly the real magic part of it, but it's like these are complex homogeneous spaces, but we're supposed to start thinking of this real thing. So it's like a complex projection. So it's like CP2, but somehow we're going to soft pedal the complex structure on CP2 in order to recognize it as S. Okay, so now you're saying what? SU3, actually SU2, it's like a right, okay, right. So okay, now I think I sort of am remembering that these partial flag varieties are really just conjugacy classes in the compact group or something like that. Yeah, the conjugacy classes in the compact group are related to these partial flag varieties for the holomorphic group. And so you're just telling me that this is just, a pretty, let's see, we're in SU3, so it's like this is a conjugate class where things just have, one of the eigenvalues has multiplicity 2 and the other one has multiplicity 1 or something like that. So you could make those two eigenvalues be like 1 and -1 or something like that. And
yeah, or 1 and 0 and think of it as a
projection.
Projection, yeah.
Yeah, but that's how you recover the original. That's how you cover the original holomorphic picture. And those projections aren't isometries. I was saying in the isometry,
okay.
in the isometry group, you put in 1 and -1 or something like that.
Yeah,
And you can actually get a conjugate class in the compact group this way. But maybe you're going in a slightly different direction. But there are all these.
No, I was just thinking about matrices right then and forgetting about them being in the group. Yeah. Which is, I guess, somehow okay, but yeah. So yeah, so you get that.
Yeah.
I mean, I will just say, I can't resist saying that, like, you also get all these homogeneous spaces, SUN mod SU
n minus 1.
Actually, it was going to be like a modulo product of 2 SU. Like
sure. Okay. Yeah.
K times SUN minus K, that kind of thing. What's that called? That's like a
Grassmannian. What?
Grassmannian. Yeah.
Well, sorry. What's the subgroup called?
No, just a.
What's the homogeneous space called? Grassmannian or something?
Yeah.
If I'm picturing it the right way, this Grassmannian. Yeah.
So well, in this particular case, we're not. So I'm saying that, like, if you take a picture for, like, you drew.
Sorry. I may not have said that right. I mean, again, I'm getting confused between the compact case and the holomorphic case. Again, in the holomorphic case, you just have these single subspaces, but then in the compact case, you also take its perp. So that's where you get, the compact thing has just this product instead of this nilpotent detritus attached to it or something like that.
Yep. So
I was just trying to confess to a mistake there. I wasn't trying to.
well, I haven't thought about this stuff for a while either. So but anyway, my main point though is that like, so like for this A2 case, you don't get a lot of different things that way. Maybe you get
okay.
for the A3 case, you'd get more already. That is, you'd get like you get different Grassmannians, and they're all symmetric spaces.
All Grassmannians are symmetric spaces. I guess I should have remembered that if it's really true. But that's making me worry that you're getting, 10 different doubly indexed series or something like that.
Some of them are doubly indexed, and the ones that are just these are different Grassmannians. Yes, so some of them are doubly indexed, and this is
one of them are doubly indexed families. Okay, that's I guess that's encouraging. Okay, so that general story that you're telling me is encouraging me to think that maybe this diamond cutting thing really does have enough variety that maybe we will get 10 different families this way if we take into account all these things that you're saying now. I mean, I'm tempted to go home and try that again. The way I'm thinking of this is that this is a counterpoint to the discussion that you've been leading. I could try to ignore all the revelations you've been giving and just go and try to approach this problem, the problem of classifying infinite families of compact symmetric spaces, see if I can use these very primitive diamond cutting techniques to get it to work. And then as an afterthought, compare that to see how that compares to your story. I mean, but again, you've already given away very many hints about how it is going to compare to your story. But that's fine too. But so I'm sort of happy now with this fragment of the discussion. Maybe we can declare the end to this fragment of the discussion. This was our little diamond cutting expedition. Do you have more to say about this before you want to try to say other stuff about compact symmetric spaces?
Nope. Yeah, no, I'll review what I once wrote about this stuff, because
what you once wrote about which stuff? The diamond cutting stuff or the other stuff?
This diamond cutting.
Are you staring at 193 right now?
No, I'm not. I'm mentally staring at this review of a book by Conway and Smith on the Octonians.
Yes.
Where I said a bunch of the same stuff that you probably were reading about the E8 case and how you can you can do diamond cutting there, and how when you get a 3-graded Lie algebra that you get a Jordan algebra of it. And stuff like that. So anyway, I haven't thought about that in relation to what I'm thinking about now.
Yeah, so let me just one more comment, which is that, like I say, these things that fall neatly into 3 pieces, those are really interesting because they give these symmetric spaces basically because they don't have any non-trivial invariant distributions. But on the other hand, if you take the opposite attitude and go looking for interesting invariant distributions, then your gem will fall into 5 pieces or 7 pieces instead of 3 pieces. And that's really fun too, but it's sort of like the opposite, complementary topic to the topic that we've been looking at, which is try to avoid having non-trivial invariant distributions on your homogeneous space. So that will cause it to be very symmetric. That will cause the action of the stabilizer that will cause the representation of the stabilizer on the tangent space to be irreducible or something like that. So sorry, that was just a comment I meant to throw in, but
just for some imaginary listeners, you mean distribution in the sense of like bundles of the tangent bundle.
Yes. If you do this with G2, you get this little thing that's 2, 1, 2, but that means there's a 2, 3, 5 distribution on your G2 thing, and that's a fun, famous distribution.
Yep.
Okay.
Let's see. I don't know if it makes sense for me to like again ask you not a rhetorical question, which is like, why are these two constructions of symmetric spaces both giving the 10 families of symmetric spaces? That was a question that I asked you.
Yeah, did I give a very weaselly answer last time? Because I'm tempted to give a very weaselly answer this time.
Right. Well, yeah. Or else I would be asking it again. But I was thinking.
I mean, I think I should think it's, I don't understand it well enough to give a good answer, but there should be a really straightforward answer, because they're just like inverse things in this Brauer group or something like that. Sorry, go ahead.
Yeah, maybe I will do it. And I think I have some stuff that I can say that makes it worthwhile.
Okay.
Different than last time.
Okay.
I'm gonna stop sharing your screen.
Sure, that's fine.
The screen because I don't have a tablet to use. I'm gonna stare at this stuff. So, okay. Yeah. So one of your answers had to do with things like.
Sorry. Just so I can fully pay attention, I just want to write down the one big magic thing that you told me that I hadn't thought of. And you were you're telling me that there may be doubly indexed families involved. I just want to write that down in my notes to really think about that. That sounds really important. It's really important for my way of trying to make sure I'm understanding what's going on. Okay, I'm done. I'm sorry for that interruption. Sorry, okay. Is the audio okay?
It's lousy.
It's lousy. Okay.
I turn off my video. It's my system's low resource.
Oh, so I can blame that interruption on the fact that you turned your screen sharing on and that caused the bandwidth problems. Okay.
Yeah. Okay. So this bold-faced thing here is is the second way of getting a big bunch of symmetric spaces that I described. And so I want to think about it more. So you have picked a star representation of the Clifford algebra with k square roots of -1 on some real vector space, and then you're trying to extend it to a representation of Cliff k plus 1.
Yes.
So you're trying to figure out, you're trying to get one extra or skew adjoint orthogonal transformation. That's what one of these. That's what square roots of -1 act as on our end. So you're trying to get one extra one that anti-commutes with all the previous ones.
Right.
And so you get this nice list of symmetric spaces that way. And for some reason here I listed actually here I described two of them. These are, by the way, are two of them that are related to doubly indexed families of symmetric spaces, because these two guys here are unions of symmetric spaces. They're not symmetric space. I said there's symmetric spaces, but that's not always true. Sometimes they're disjoint unions of symmetric spaces, because sometimes the choice of ways of extending your star representation sort of breaks up into quite different kinds of ways.
A union of symmetric spaces, a disjoint union of symmetric spaces.
Yeah.
But is there you're sure there's not like a discrete involutory quandle structure on the components of that thing? Maybe it is a, I don't know. I'm just imagining there might be something slightly better than the way you said it, but I don't know.
Well, it might be. Maybe who knows? I mean, this one here. There's also one for the unitary group, by the way, and that's the one that we were. There's one that looks like this with U's, and that's the one we were sort of almost talking about. So I could ask you, do you know such a structure on the space of all subspaces of a real vector space or a complex vector space?
All subspaces of a real Euclidean space?
Yeah, for example. Yeah.
All linear subspaces of a.
Yeah. So if you fix it,
why wouldn't there be? Am I screwed up?
What is it? I don't know why that's like.
I mean, you're saying that. Why are you saying that there's multiple components in this example? Why are there multiple components?
The disjoint union of a bunch of Grassmannians. These guys here are Grassmannians of various d-dimensional subspaces.
Oh, you're getting something like that. Oh, I thought you were getting. Okay, let me think about that. Let me think about that. Well, yeah, I hope it's sort of obvious. Am I screwed up here? I mean, it's. Yeah. I mean, this is a straightforward part of the David Joyce quandle business. I mean, right? I mean, this is you have what am I trying to say?
What I'm saying is I know how to.
I mean, you've got a non-homogeneous space, but it's active. You've got an action of the group, and it's got these separate components. But this this action is included. This action is equipped with an equivariant map to the conjugation action of the group. And that, am I doing the right thing here? That in order to get any subgroup to act on any, in order to get any subspace to act on any subspace of possibly different dimension, it's straightforward because the subspace acts on the whole ambient space.
Oh, okay. So let me just, for the benefit of anyone else.
I'm not saying it well, but.
And I'll just say it. So like if I have I'll just also to confirm that I'm understanding it correctly. So if I have any subspace of Euclidean Rn.
Yes.
Then there's a linear transformation that's the identity on it and -1 on the orthogonal complement. And so that helps to map subspaces of any other dimension to other subspaces of that dimension.
Yes, there's an induced action on subspaces, and it just doesn't care what the dimension of the subspaces are.
Okay, great. Yeah. So
and it's also worthwhile, as I say, looking about how that actually fits into the theory of quandles, and it's even mentioned in the original quandle paper.
Okay, so these are quandles then.
Yes, they are involutory quandles.
Involutory.
And they're the kind of involutory quandle where each quandle orbit is a component or something like that. So it's actually a disjoint union of symmetric spaces, but you can actually reflect one component across another as well.
Yep. Okay, well, that's nice. Yeah, so we get these things, and these, so there are these two cases and one other case, which is the U case, and those are the cases that are associated to doubly indexed families of symmetric spaces. That is, so you've just said, well, there's singly indexed families of involutory quandles still, but
well, that's interesting. Yeah, I have to go home and think about that aspect of it, how this doubly indexing thing relates to the separate components thing. Yeah. I mean, it sounds like.
Well, anyway, so it's good that I showed you this because that makes the story sort of nice.
Yeah. I'm just putting this in my notes. Go ahead.
But what I was wanting to do was, which I probably should have done on my own, but I've been too busy with other things, is to think about this bold-faced idea in a more sort of abstract way.
Yeah.
As like an example of a general kind of thing. So like
it really wants to be thought of that way. It probably wants to be thought of in other ways too, but it really wants to be thought of in that way. Yeah, go ahead.
Yeah. So one reason why it's so worth thinking about is that in other aspects of the tenfold way, we are very interested in these categories, namely category of all star representations of a Clifford algebra.
Yes.
Well, here, I don't know why, but I just sort of feel like showing you that again. So we get these categories here. Here, I was not really talking about star representations. I was just talking about representations. But I could, if I wanted to, talk about star representations, and then it would just change from something like real vector spaces would turn into like real vector spaces with orthogonal structure.
I mean, this sounds like another instance of the unitary trick.
Oh, yeah, maybe.
No, we don't have to worry about that, but it does sound like that. Go ahead.
So anyway, so one very nice aspect of like Bott periodicity is that you get the circle of 8 categories, which you could think of as categories of star representations of Clifford algebras. And because of the periodicity, you get back to the same category after you loop around, after you add 8 to your dimension of your subscript here.
We weren't that decided that we want it to be a category rather than a groupoid, right? We thought it might be a groupoid or a topological groupoid, or
well, I don't mind that. That's fine. Yeah, I think that makes these adjunctions not adjunctions anymore, but still, it's for plenty of purposes. You might want to have there be think about.
Okay. No, but thanks for reminding me that we may very well want to try to make those adjunctions into category-theoretic adjunctions. So, okay, that's a good point. Okay. Again, I'm not sure exactly how to do that, but that's a very good possibility.
Yeah, so I would keep an open mind about that.
Sure.
So then, but if you just think of them as the groupoids, for example, then in some ways that's very natural too. And then these, you have these forgetful functors. Well, they look more forgetful some places.
Actually, now that I think about it, it really does look like you got categories here. I mean, I was probably thinking of some other thing where you just maybe have groupoids, but here it really does look like you have categories, I think. You know, representations of a Clifford algebra, that seems a very decent category. Sorry, I'm just trying to follow along here. Go ahead.
Sorry, I can't hear you.
I
didn't hear what you said just then.
Oh, it's just a momentary. Okay, I was saying that I was reconsidering, and I think that you really do have categories here, because you know, categories of representations of a Clifford algebra. That really is a very decent category.
Okay.
You know, there may be some other context here where I might want to, you know, work with groupoids instead of categories, but in this context, I think you're right that we probably really do want categories here, and the adjoint functors, and, you know, categories of representations of Clifford algebras. That's perfectly respectable.
Okay, so then So then we have these functors, which are pointing up in this picture, which are forgetful functors.
Yes.
And so then, so they're very nice things. And so then the thing that I was talking about on the other slide was how we get some spaces out of those, namely, like I take a real vector space and I get the space of complex structures that I can put on it. Or I take a complex vector space and I get the space of ways of extending that to a quaternionic structure, and so on and so on.
Yeah, that might be where the groupoids come in. Yeah.
Yeah. So for some reason or other, I never really thought much about spaces of structures you can put on an object. And so I was sort of hoping that you would somehow help me think about those. And in particular, I mean, ultimately, what we sort of want to understand in this case, or what I want to understand in this case, is why the spaces of structures that we get, are actually are symmetric spaces.
Well, again, I mean, what you're talking about is almost, spaces of structures is almost synonymous with homogeneous spaces. And homogeneous is a start towards symmetric. I mean, that's the very naive idea.
Well, that's good.
And then the diamond cutting thing, for example, is a primitive way to start trying to think about, or a very special way of trying to think about making progress from homogeneous to symmetric, which is like really, really homogeneous or something like that.
So sorry, this is, I know I've never succeeded yet in getting you to answer this question.
Yeah.
Well, I'll try again.
Try again, yeah.
Like sort of so embarrassing that I should almost just like answer it myself. But, but like suppose you have a forgetful functor from some category to another.
Yes.
Groupoid to another.
Yes.
Then like what's your story for how you like think about, how do you describe this space? Maybe it's a category where that you have Hom spaces instead of just Hom sets. So then it seems like you need some kind of spaces to get into the game somehow like that. And so then what's the way that you like to think about the space of structures that you could put on an object of the base category?
Again, I think I did sort of answer. It's like a homotopy fiber. I mean, again, you have to think about different meanings of homotopy fiber.
Well, you said, okay, but can you explain that?
Yeah, okay, I'll try. Maybe I'll try to steal the screen from them.
Yeah.
Or maybe you can,
you
have to give it to me or something like that.
I'll give it to you, yeah. Maybe I do know what you mean.
But let me take a stab at drawing something to. Okay, so I've got.
Gotta share your screen.
Yes. Okay. So what am I trying to say? So we have a category. Let's say we have a functor f going from, I don't know, C to D. And you've got, let's say, an object D1 in D. And I mean, it's somehow lurking in the background here are words like comma category, but it's really probably more like comma groupoid or something like that. But it's related to, homotopy fibers. These are all, a comma category is some sort of lax homotopy fiber or something like that. That's what a slogan you hear sometimes. at least some, sorry, some common categories are lax homotopy fibers. Let's see. But yeah, so what am I trying to say? I'm trying to say we want to consider diagrams that look like C1, sorry, F of C1, and then an invertible map J to D1. And
can you just draw a little isomorphism-y symbol next to the J just for my?
Yes, I was actually going to put little like backwards arrows. Is that good enough?
Okay, that's weird, but okay.
You were hoping for something like that or something like that?
Yeah, it's okay.
So yeah, so I mean, the category of diagrams that look like this. So this is, so, and we have another one, F of C2, let's say. And this is F of M or something like that. So what am I trying to say here? So let's see. Right. So okay. So right. Maybe you do want. Let's see. Let me think what you're saying here. Let me think what you're saying. So enriched over. Okay. Yeah, there are interesting questions here. You may need a category object rather than just a category enriched over topological spaces or something here. Let me think. If you're really trying to get a space out of this, let's see. Yeah, I mean, well, certainly if C and D are topological groupoids, let's try it that way, okay?
Does that mean internal or enriched?
Means internal.
Okay. Okay.
C and D are
in our example, I mean, would you think of like the category of vector spaces? I would normally think of that as just enriched. I mean, you can think of it as internal is more general, I guess. So yeah.
Internal is, well, more general maybe, but there often are very interesting ways of the examples that you're talking about. There probably are ways to think of it as internal or locally internal or something like that. What is this reminding me of? It's reminding me of like certain versions of stacks and things like that.
Yeah, I'd been thinking of it as just enriched, and so I'd been thinking that like this space would somehow just be coming out of the fact that we have spaces of linear transformations of different kinds.
But
I'm open to hearing whatever you want to say.
Yeah, I mean, I'm saying that we may have different objects C1 and C2. It's like it seems like you're trying to get away with, and you may be able to, cut corners and get away with having C2 be the same object as C1 or something like that. So you're just dealing with a single Hom space.
I will say that like in these Grassmannian, in this thing we were just talking about, this doubly indexed family business, that's a case actually where I think I'm confused, but it seems like that's a case where actually we have to worry about multiple objects. Yeah, I think it is. So that is, I think there's a case where like the way it is like C is like pairs of vector spaces and D is vector spaces and F is direct sum. And then and then from that,
that may be true. That may be true. But it sounds like you're also saying, but you could still might be able to cut corners in that case because you're going to have those things in separate components.
Yep. Right. So that seems to happen in my examples. Yep.
Yeah.
But anyway,
let me just give you one simple case where C and D are internal categories in some nice category spaces, F is an internal functor between them. And then you can do things like, take the things that look like, what am I trying to say? F. Let's see. F of C. One. I mean, and then you would end up getting a space of diagrams that look something like this.
Mm-hmm.
But that wouldn't end up just giving you the space that you're looking for. I think it would end up giving you a groupoid, another topological groupoid or something like that. And you might need to take like the isomorphism classes of objects in that groupoid or something like that, like a coarse moduli space or something like that.
Right.
So yeah, okay, there are a lot of tricky questions here that I'm not really prepared to give good answers to really at the moment. Which is probably the same thing I said last time.
No, this time it was much better. You said you concluded the same way last time, but this time you gave me some diagrams and something to chew on that, well, I wasn't able to extract that from what you said last time. So
yeah, okay.
Yeah, so right. So the interesting thing is that it seems like in tons of in 7 out of the 10 cases that I'm interested in, you can pick a particular object C1 and take just the set of morphisms from F of C1 to D, or the space of morphisms from F of C1 to D.
Yeah.
And that happens to be the space that I'm after. And then in the other 3 cases, I guess it works that you have this set of objects, different objects for C1 that you need to consider, non-isomorphic objects C1 with maps from with isomorphisms from F of C1 to D. And then you take the disjoint union of the Hom spaces. And those are these Grassmannian cases we're talking about.
Yeah.
But both of them seem it just sort of those are simplifications of some more general, less ad hoc construction.
Yeah. I mean, they're right. There probably are, quick and dirty ways of doing this, and then there are more morally correct ways that might actually be worth thinking about.
Yeah, I do want to. I mean, I think I can do the quick and dirty ways. So I was sort of hoping for the slow and clean ways.
And I'm saying that may very well be worth thinking about, but I do have other stuff that I want to talk about.
Okay, yeah, okay, fine. So we can quit here then.
Okay, that seems like a good place to quit. And let's see, should I take a recording break so I can set things up? I'm probably almost ready, but maybe a recording break would help.
Okay. Last time I stopped the recording by accident, and then I had to glue together 2 videos.
Right. Maybe you can. Maybe have you learned how to do pause yet?
Yeah, I learned. It's motivated me to.
Okay.
Okay, we're back.
Okay, so I'm going to try to talk about some Gaussian design stuff now. This is aspect of this Grothendieck-Teichmüller story. And let's see, am I sharing screen now? Yes, I am screen. That's my screen. Yes. Okay.
Yep.
So it's sort of the usual story that I claim I have this big conceptual story picture that I'm trying to tell you about, but what I actually end up telling you about is some very specific examples, and we look at them in detail. I mean, that's what we're going to do today, for the most part, unless we're really, really lucky and get to talk about the big picture. But I'm going to show you some detailed stuff about the same examples that we've been trying to understand, because now I understand them in even greater detail. And secretly, it is telling us about all this conceptual big picture. But, you know, we'd have to be really lucky to get to be able to say out loud any of this conceptual big picture. So let's see. So what am I trying to say here? Okay, maybe, right. I should switch from my notebook here to show you my Mathematica. Yeah, unfortunately, I'm still in this situation where I have to switch back and forth between the Mathematica stuff and my notebook stuff. So now you can see
Yep.
the Mathematica stuff. And you can see the, right, the ridiculous symbolic algebra that Mathematica does, but in the service of understanding these pictures of Gaussian designs that are apparently in the same Grothendieck-Teichmüller orbit. So, yeah, so you know, now I'm sort of trying to remember what the story was so far, where we got to. And I think we basically got to the point where I was trying to impress us both with the fact that Mathematica did find the symbolic solution. And that had a lot to do with, like, there were lots of formulas here with the square root of 3 in them. You can see a lot of the square root of 3 in there. And you know, so a lot of what I was doing last time was just struggling to make concrete sense out of, you know, what is the square root of 3 doing in there? And I had the feeling that I shouldn't trust Mathematica, right? Mathematica is printing out these ridiculous formulas, just ridiculous. And it deliberately tries to do that. It thinks it's impressing us by printing out these ridiculous formulas.
What's G, by the way?
What?
What is G, by the way? I just noticed.
Yeah, G, I guess you can see some places where I have changed G to a constant. I think in this, this thing here, you can see that G has been replaced by a constant. Yeah, G has been replaced by the constant 1 here. G is, it just has to do with a certain degree of gauge freedom that has to be dealt with, but it's probably not very important. It's you know, the fact that the fractional linear transformations are acting on the Riemann sphere. The Möbius transformations are acting on the Riemann sphere. And, you know, the designs can be moved around by these Möbius transformations. And setting G to 1 was just a way of nailing down a point on the Riemann sphere. And so it's not really important. And you can see that even after I replaced G by 1, there's still these ridiculous square root of 3 things in there. And you know, so I'm trying to understand these algebraic numbers, right? This whole Grothendieck-Teichmüller theory has to do with absolute Galois group, which is the symmetry group of the field of algebraic numbers or something like that. And so, you know, we're really trying to understand these algebraic numbers here. And Mathematica is printing out ridiculous symbolic formulas for these algebraic numbers. And I think I was right to not really trust what Mathematica is doing here. It's not really, you know, it's trying to print things that make it look impressive, but it's not really succeeding in doing it the right way. And so I only paid half attention to what Mathematica is doing, and I tried to figure things out by hand, and it's, you know, sort of annoying in ways. But I managed to make more sense out of what is going on here. And so it turns out that what is going on here is not only is the square root of 3 involved here, but the 4th root of 3 is involved here. Or as a matter of fact, it's probably better to think of it as involving the 4th root of 12. You know, so I'll be trying to tell you about some numbers here involving the 4th root of 12. And in fact, the extension field, the Galois extension field, is that what it's called? The Galois field, Galois subfield, Galois field, Galois extension field that we'll be dealing with here is going to mainly be the splitting field of the 4th roots of 12. So that's that's a certain, I guess it's called a degree 8 extension of the rational numbers. And we'll try to figure out why it's degree 8. And saying that it's a splitting field, that's probably near synonymous or very related to saying that it's a Galois field or something like that. But it's also secretly just saying that, you know, we have this Galois group and we have it acting in such a way that it's acting in the Torsor picture rather than in, you know, some other action or something like that. There's all sorts of ways of thinking about this. I wish I had a better facility to say how they're all related to each other. But so yeah, so it turns out that all these pictures are in some sense based on the splitting field of the 4th roots of 12. And we're going to try to understand that in a concrete way. And secretly, it's going to tell us a whole lot about understanding the abstract big picture. But we're mostly going to try to understand in a very concrete way what's going on here. So, so first of all, I sort of semi-predicted something like this many weeks ago, except that I probably got it slightly wrong. So, I mean, these 4th roots of 12, for example, so, you know, studying the algebraic number theory of 4th roots, that has to do with quartic reciprocity. That's what quartic reciprocity sort of means. The algebraic number theory of 4th roots. And this has a lot to do with the Gaussian integers, in the same way that the Eisensteinian integers have to do with cubic reciprocity. So, I mean, what's the idea? The idea is that, right, there's an ambiguity whenever you're talking about 4th roots of a number. And the ambiguity is you never know which invertible Gaussian integer you might have multiplied by. Right, if you take a 4th root of 12, for example, and if you multiply by 1 or I or -1 or -I, that you get another 4th root of 12. You get something that's algebraically indiscernible from the original. So that's an important part of the Galois action here, the Galois ambiguity here. So that's kind of saying that when you're studying quartic reciprocity, when you're studying 4th roots, it's a handy thing to first take the Gaussian integers and do all of your work over the Gaussian integers, because then, you know, all of these indiscernible partners of a 4th root will be right there. There'll be something that you can talk about rather than having to extend further to get them. So it's, you know, I mean, there's a bunch of ways of saying what this is doing this, but I guess one way to say it is that once you have the Gaussian integers in your base, then adjoining a 4th root of a number is just an abelian extension. It just has this size 4 cyclic Galois symmetry. And that corresponds to simply, you know, multiplying by 1 or I or -1 or -I. The same way when you're doing when you're taking a square root or any quadratic extension, well, specifically when you're taking a square root, you know, the Galois ambiguity, the Galois symmetry, the Galois action is always just the Z mod 2 that comes from multiplying times -1. So, right, right, what can I say? So that the 4th roots of unity act on the 4th roots of anything else. That's what I should have said. Just like the square roots of unity act on the square roots of anything else, or the cube roots of unity act on the cube roots of anything else.
Yeah.
So if you're going to be playing around with 4th roots, it's a good idea to throw in the 4th roots of unity, because that'll make things simpler. So,
so are you hinting
yep.
that all Gaussian designs are somehow linked to quartic?
That's the sort of optimistic prediction or optimistic guess I made many weeks ago. And it's being somewhat confirmed, but confirmed in a somewhat weak way. It's probably being confirmed in a way that's maybe different, slightly different from the way I was expecting. But it's certainly true for this doublet. That this doublet is really, really explained by this quartic reciprocity thing, specifically the fourth roots of 12. Which involves, the fourth roots of 2 and the fourth roots of 4 and the fourth roots of 3. Fourth roots of 4 is mostly just the square root of 2 or something like that.
Okay, so I'm all ears. So how is it?
Yeah.
How does it work?
Like I say, if you start from the Gaussian integers, then you're just getting this. Then it's just a fourth degree extension to go to the fourth roots of something. But if you start from just the integers or the rationals and you go to the fourth root of something, and you take the splitting field, then you're gonna throw in you're automatically gonna throw the Gaussian integers as well. Because if you divide one of the fourth roots by another fourth root, you'll get I. If you choose the right ones or something like that. So in the splitting field, you're definitely going to have I. It's going to be there. What am I trying to say? That right? If you start from just the rationals, then you're going to have this 8-element Galois group. And if you think about that, that's going to be dihedral. That's going to be, this semi-direct product of complex conjugation acting on. That Z mod 2 given by complex conjugation, semi-direct product of that acting on this fourfold ambiguity of fourth roots that comes from multiplying by a fourth root of unity. And so, a lot of what we're going to try to do today is sort of trying to understand how the practical Kleinian geometry of the dihedral group impinges upon this Gaussian doublet. And one of the things that we need to try to understand there is that, it sort of seems like, if I understand correctly, this Gaussian doublet, it's like the absolute Galois group is acting on this pair of Gaussian designs. It just flips back and forth between this one and this one, basically. But, so that sounds like it must be some 2-element quotient group of the some 2-element quotient group of the dihedral group. So there's this Galois, the dihedral Galois group, 8-element dihedral Galois group of the splitting field of the fourth roots of 12. And somehow that's going to be acting not faithfully on this pair of Gaussian designs. And we want to try to understand how that works and everything. And like I said, it involves, to some extent, the practical Kleinian geometry of the dihedral group. So, and again, for the general Grothendieck-Teichmüller theory, we want to understand why the Galois group why the Galois group that's involved here may be acting unfaithfully on the Gaussian designs, or more generally on the designs in the case where going beyond just Gaussian design. And so one of the themes that's going on here is that the absolute Galois group of the rationals is going to be acting on the designs, but it's also acting on the vertexes in the designs. And so sometimes you're going to have some part of the Galois group that takes the design to itself, but it doesn't take the vertexes in the design to themselves. It permutes the vertexes within the design. So that's kind of part of we have to try to understand, and that's going to be significant in trying to understand the general Grothendieck-Teichmüller theory. I mean, in the general Grothendieck-Teichmüller theory, we're going to have these sort of braid-like groups that are acting on the sort of profinite versions of free groups, and So we have like a group that's acting on a group, but we're going to think it in terms of a group acting by functors on the representation theory of the group, or acting on the set valued representations of the group. So we're going to have a group acting on a groupoid, and there's going to be some sort of like coherence issues involved in a group acting on a groupoid. And that's involved in the idea that, like I say, sometimes we're going to have a group element that takes a design to itself, but that it doesn't take the vertexes in the design to themselves. So it's like a sort of coherent thing going on in some very vague sense. You know what I mean?
Maybe. I mean, there's sort of two things run. I don't know why you call it coherence, but there's sort of like a group. There's a groupoid. There's a thing of designs, and there's a thing of like labeled designs that are. I hadn't really thought about much. So you're
yeah,
saying.
and some and some things are going to be more faithful. I mean, right, you get more faithfulness if you work with the labeled designs or something like that. And so that's an aspect of we have to try to understand. So one of the things that we have to do is we have to give individual names to the vertexes in these designs.
Is that what is that the thing that flickers on? That's the name there.
I guess that's right, but I'm gonna, use simplified names like A and B and C. So there's an A, B, C, D, E, F, G, H in this design, and there's an A, B, C, D, E, F, G, H in the other design, and they're sort of secretly the same, but we have to, and so okay. So first of all, let's think about this splitting field. And as usual, I'm very disorganized here, so I'm, going all different directions at once. But one of the directions we want to think about is, let's think about this Galois field that I'm claiming we should be thinking about. We should be thinking about the splitting field of the fourth roots of 12. So let's just call K be our favorite fourth root of 12. Now, often when I say,
Are you writing on something that I'm supposed to be seeing?
Yeah, this is where I'm supposed to switch back and forth. There is some way you can sort of show two screens at the same time, but I'm not competent to do that yet. So yes, I should be switching back and forth. You should always remind me, I think, whenever I seem to be talking about something that you can't see. Am I doing this right? So now you can see where I'm writing?
Yep.
But it's very hard to read my handwriting anyway. So
Favorite.
it says K is equal to your favorite fourth root of 12. Now, very often when I say, your favorite one, that means privately you should choose one and don't bother me about which one it is. But in this case, it's such obvious what the favorite one is. And that's part of the mystery, right? Well, how can there be this algebraic symmetry between the fourth roots of 12? And yet the symmetry is broken by the fact that we all have the same favorite one, which is the positive fourth root of 12.
Right.
So, somehow it's analytic things that are breaking the symmetry, or at least that's one way to think about it. So that's very roughly equal to 1. If I'm not misremembering too badly, it's 1.86 or something like that.
Okay.
And so in the splitting field, a typical element looks like P plus Q times K plus R times K squared plus S times K cubed. And that's all you should take, right? If it goes up to K to the fourth, then you just got something rational again. But moreover, this, P, Q, and R, S, and R and S here, these should be in the Gaussian rationals. In the Gaussian rationals. Right, so that's an 8-dimensional extension field of the rationals. That's what they look like. And concretely, we can work with those. And what I'm pretty much claiming is that if you look at all the vertexes in this other picture, let's see how quickly I can switch back and forth. I got to get better at this. All those vertexes are those are numbers of that form, numbers in that field, that splitting field. Like so this one right here. So it kind of looks like there's 6 vertexes in this design. Do you agree?
Yes, 3 on the left and 3 very similar ones on the right.
Yes, but there's actually 8. There are 2 invisible ones. And the way you can tell that there are 2 invisible ones, one of the ways you can tell that there are 2 invisible ones, is that the all the regions in this picture are supposed to be basically 2 simplexes, basically triangles. But there's a few of them that don't look terribly obviously like triangles until you put in the invisible vertexes. So like, right, there's this one here, it looks like it's got 2 sides. This one's got 2 sides. These ones here, it looks like have the 2 sides until you put an invisible vertex right there, and somewhere right there in the middle, and somewhere right there in the middle.
No.
So
what about the southern exterior region that has more than 3 sides?
I think it's got 3.
Oh, okay. Sorry, because the left thing is the same as the right thing. Yeah.
Yes, because the point at infinity is not exceptional at all in this picture.
Okay.
It's the perfectly ordinary point on that thing that looks interrupted. So at least I hope that's the way it's supposed to be interpreted. So yeah, let's try to figure out what these points here. So there's A, B, C, D, E.
I think you got to change over again.
Yes, thank you. You'd think I'd get quicker each time I do it.
Well, we'll see.
Okay. A, B, C, D, E, F, G, H. And we're going to have a kind of table here with their P, Q, R, S values. Again, so right, a big part of what I'm telling you today is just that this seems to work, in a very clumsy way. I managed to actually figure out what these alleged algebraic numbers are. They are in this splitting field. And it makes a lot of conceptual sense that this splitting field is the field that's involved, because this involves quartic reciprocity. So by the way, so yeah, this is all based on the prime 3, if you recall. These diagrams, came from these things that really involve the Gaussian integers mod 3. Whereas you can also do the Gaussian integers mod 7 or lots of other examples. So I'm sort of guessing that if you do the Gaussian integers mod 7, I'm guessing it involves the 4th roots of 28. That's just a simple-minded pattern, just like 3 involves the 4th roots of.
You know where the factor of 4 came from? So 12 is like 3 times 4. Where's that 4?
Well, I could take all sorts of silly guesses. I mean,
okay,
it could be just from the fact that I have 3 different colors of dots. My red dots, my red vertexes are coming from the Gaussian integers themselves, but my green ones are coming from the deep holes between the Gaussian integers. So I'm sort of like doubling up. So that halfway accounts for why there might be a factor of 4. That's like an extra factor of 2 or something. I don't know, something like that. There are plausible reasons why it might show up. But I also want to confess that I think if you do the the one that involves the Gaussian integers mod 7, I think it's going to be a little bit worse than just the 4th root of 28. I think the 4th root of 28 probably will be involved, but I'm guessing there's going to be some worse irrationalities in there too. So I don't know, and and to a great extent we want to avoid having to think about details like that. But I never do actually avoid thinking about details like that. But well, anyway, we're really thinking about the details for this Gaussian integers mod 3 one. But
okay,
we would like to have more elegant techniques that will generalize to Gaussian integers mod 7, mod 11, et cetera, et cetera, et cetera. So Right. So, part of what's supposed to be good here is just the fact that in principle, I can tell you what all these numbers are here in this little table. So let me see if I can do some of these. Let me see if I can copy some of these from my notebook here. Well, let's see. So first of all, there's a kind of, let's see. So these are, right. Right, I'm not following my own philosophy. I mean, I like having colors here. Colorblind people don't like that, of course, but I like having colors. But I'm being so disorganized and lazy here. I don't have the colors here, but I'm supposed to have A and B are supposed to be green, and G and H are supposed to be red, and the 4 in the middle are supposed to be blue vertexes. And there's this kind of palindromic red-green symmetry. And again, this is the duality between the Gaussian integers and the, what do we call them? The deep holes between the Gaussian integers. So in the red-green duality, the deep holes and the Gaussian integers switch. So the green goes to red, but the blue are kind of neutral between green and red, and they, blue goes to blue or something like that. So, in other words, one of the things is that the work of filling out this table is, presumably half done automatically by this red-green duality symmetry. And there's all sorts of duality symmetries floating around here. I mean, we've got this dihedral Galois group. So, there's complex conjugation, and there's.
Is that dihedral? Sorry, is that twofold symmetry that you just outlined? Is that the super visible twofold symmetry in those pictures that you showed me? Is that a different one?
Say that once again. Is which one the visible symmetry?
This symmetry here that you just marked with all these semicircles.
Yeah.
Is that the same as the visually most evident? I hope there's one visually most evident Z mod 2 symmetry in those pictures you showed me. Because otherwise, then we have like 4 symmetries right off the bat.
There's something very left-rightish about this. It may be like inversion in the unit circle or something like that. I mean, that's a great question, and I don't have a great answer for. Maybe there's some hope we can answer that question by the end of today. We'll.
Okay.
But yeah, we right. I really want to be able to answer all those questions instantaneously, but I can't quite answer all those questions yet. So first of all, let's try to explicitly say what the generators of the Galois group are. Okay, so one of them is PQRS goes to. Am I doing this right? Goes to, just pointwise complex conjugate. An asterisk is okay for complex conjugation?
Yep.
And the other one is what? The other one should be P goes, well, P is going to stay the same, but we replace Q by, multiplied by I. But if we're replacing Q by multiplied by I, then R has to be like -5 or something. And S has to be -5 and multiplied by I. Does this make sense?
Yep.
So these are the 2 generators of the Galois group. And I think what it is, right, there's a picture of the 4 fourth roots of 12, and it sort of looks like this. Right over here is 1.86, and here's 1.86 times I, and et cetera.
Mm-hmm.
And yeah, so it's just counterclockwise 90-degree rotation is that generator of the Galois group. In some sense, on these 4 things, but I'm also I'm right now I'm trying to convince us that we can really think of it as intuitively like a dihedral symmetry. I mean, this is like a square. And you can rotate it 90 degrees, but you could also, I guess, complex conjugation is just flipping it like this, I guess, you know, along the horizontal axis or something like that. So that's this thing here. Does that sound right? Does that sound like what's giving? So it's, yeah, it's the semi-direct product, right? So the acting group is not a normal subgroup. The other thing is a normal subgroup, right? Okay, okay.
So you got this 4-element cyclic group generated by multiplication by I, and this 2-element cyclic group of complex conjugation, and the latter is acting on the former. Yeah.
Does that seem right? Does that seem that those, you know, commute or fail to commute, but in the correct way? They non-commute in the correct way, or they commute in the correct way for a dihedral?
Yeah, that's definitely a dihedral group. Yeah.
Okay. Okay. Yes. Okay. So let me try to tell you. Again, I'm jumping around here. I'm not quite sure what I'm doing, but let me try to tell you what part of this dihedral symmetry is, I think, accounting for the Gaussian doublet, accounting for the real radical change in shape between this one and this one. And I want to say that I think it's the 90-degree rotation. And you know, and if you do the 90-degree rotation twice, it just gets you back. So I think that's the part of the. So so I guess I'm saying that there's a quotient group. Is that right? I'm saying, what am I trying to say? So okay, so there's a 2-element quotient group where, is that right? Is there really? I mean, there are all sorts of 2-element quotient groups here, but I don't want it to be the orientations thing. I want it to be. Is this working? What am I trying to say? I'm having trouble thinking of a 4-element normal subgroup.
Of what? Of the dihedral?
The dihedral group, other than, you know, the one consisting of the rotations, because I want the 90-degree rotations to act non-trivially. Can you help here?
The 90 degrees, you want them to what? To be acted on? Or to act on? Sorry, I'm confused. But sorry, I don't get why you care about this, but
well, because I'm trying to straighten out how. Let's see. I think I'm claiming that this dihedral group, maybe it's just a subgroup of the dihedral group that's acting, but I think it's the whole dihedral group is acting on this 2-element set of differently shaped designs. And the 90-degree rotation is the thing that's changing us from one shape to the other shape. So clearly clearly I'm trying to think of what's in the kernel here, but this is in the kernel, this is in the kernel. Oh, okay. Okay, maybe this is making sense. So, okay, right. So there's actually, right, there's 2 different kinds of reflection. I was thinking there were just 4 reflections of the same kind in this, but there's really, right, there's like the reflections along a short axis of the square versus reflections along the long axis of the square.
Yeah, the diagonal of the square, you mean. Yeah.
Yeah. Yeah. And so which ones, right, so reflections along the diagonal of a square, those should be in the kernel too. So it's like, yeah, it's right. Right, the four that are acting trivially, the four that are in the kernel are the identity, the 180-degree rotation, and flipping along the diagonal. Right, and that's somehow, right? I mean, it's like, those are the four that kind of take real to real and imaginary to imaginary. Is that right? Yeah, there's a Klein 4 subgroup of the dihedral group, of this dihedral group, which takes real things to real things and takes imaginary things to imaginary things.
And you're saying that's normal?
That's a normal subgroup. And that is the kernel. Those are the ones that don't change the shape of this. Yeah, those are the ones that don't change the shape of the designs, of these designs.
I'm just supposed to believe you about that last part, right? I'm not supposed to see that.
No, you're almost supposed to see it. Let's halfway try to convince ourselves of it. So first of all, okay. First of all, it has to do with the idea that the things that change the shape of the design have something to do with changing real to imaginary and changing imaginary to real. But let's see, what am I trying to say? What am I trying to say? Well, okay, yeah, there are probably some things that you're supposed to be just sort of taking on faith there, but there are other things that are fitting together here. So, like, one of the things I'm trying to say is that let's try to understand in more detail which elements of the Galois group manage to take real things to real things and take imaginary things to imaginary things. And so I think what I'm saying is that the one that really matters is, so like we say, we're taking the fourth root of 3, but you can break up taking the fourth root of 3, you can break that up into 2 steps. First, take the square root of 3, and then take the square root of that. And it's that first step that's the key ambiguity. Because, right, the first step where you decide to choose the positive square root of 3 or the negative square root of 3, that determines whether the next square root that you're going to take is going to be real or imaginary. Right? Because if you end up taking the square root of -3, then you're going to be taking the imaginary stuff. Whereas you take the square root of 3, you're going to take. So I hope I'm saying that right. I think it makes sense to me that it's, the ambiguity between the positive square root of 3 and the negative square root of 3.
Go ahead.
That is giving us that part of the dihedral group that mixes up real stuff with imaginary stuff.
Okay.
Okay. So, there's all supposed to be propaganda for it all fitting together. But okay, let's see if we can. First of all, let me see if I can. Okay, first of all, I have to remember which one I'm screen sharing with. So you're seeing.
I'm seeing this chart that I thought you were going to start filling in, but.
Yes. Okay. Right. Let me start trying to fill in some of it here. So it should be right here somewhere. Let's see. Can I find it here? Let's see. And right, we're blindly hoping that the typos in this aren't too bad. So I think it's something like D is -J in there. Sorry, it's supposed to be -I. -I. And then 1/2 in the next one. And then I/2 in the next one. And then -1/4 in the next one. And all of these other rows can be filled out by, you know, a little bit of squinting at my mathematical results. And so there's another one here, the G here. You might remember that, you might have seen in my mathematical code, there was this place where I just set G to 1. So G is actually, you know, just 1, 0, 0, 0. And by the palindromic symmetry here, that the G is palindromically opposite the B. So I think, oh, I think B ends up being -1, 0, 0, or something like that. Something like that. And the E, I think E ends up being maybe the palindromic symmetry, maybe for some reason X by negatives or something like that. I think it does. So I think that this is, I'm guessing it's, you know, I'll call these typos if they turn out to be wrong. But I think it'd be like this. I, and then -1/2, and then -1/2, and then +1/4. Does that really look right? Let me check my. All right, again, there is already a typo there. This is actually right. This in the third column here, that's not a 1, that's an I. And that means that this is also an I there. So hopefully it's like that. And now I also had C here, but I think there's a typo in C. I had for C, I had 1/2 and 1/2 and 1/4, but I don't think that's quite right. I think there's some, let me put like a question mark. That's probably a little bit wrong, because I don't think those are supposed to be real in C. When I stare at where C is in the picture, it doesn't look like it's on the real axis or something like that. So I think that's probably wrong. But okay, right, again, this is all propaganda for convincing us that reasonably nice things are happening. So one of the reasonably nice things that are happening here is that, first of all, the denominators are not very scary at all. They're just like 2 and 4 in the denominator. And they're even unscarier than that, right? Because we're sort of used to the idea that when you're dealing with algebraic integers, you know, there's like a lattice of algebraic integers, but sometimes it's like a little bit bigger than you're expecting. Like sometimes, you know, you have a lattice and then the deep holes of that lattice, they actually turn out to be algebraic integers there as well. And so it's like twice as big or 4 times as big or whatever as you were expecting. So, right, I guess that I'm guessing that all of these numbers are in fact algebraic integers for some reason, which makes it a little bit more pleasant to deal with. Yeah, so I don't have quite all the rest of these to fill in for you, but that's only because I'm really lazy and disorganized. We are really getting a very explicit description of these Gaussian designs. We're getting a very explicit description of these Gaussian designs, and it is all contained within, in some sense, the splitting field of the 4th roots of 12, which makes very good sense because of the quartic reciprocity aspect of the Gaussian integers. Yeah, so I mean, in some sense, right, there's good, manageable raw material to try to understand for this example, to try to get it to make sense in the general theory. So, you know, that's kind of what I'm trying to say. Let's see. So, once again, I should be able to tell which screen is showing here. You're seeing the silly chart with the numbers in it, right?
Yep.
Okay. But let's see, right. I really like to get better to the point where I can show them both at the same time, because I really want to show you how the letters in the letter names for the vertexes that I'm writing on this notebook here correspond to the Mathematica pictures. I guess what I'll try to do is I'll just try to quickly sketch what some of these pictures look like in the notebook here, and then put the letter labels on them or something like that. So let me see if I can come anywhere close to sketching this. So it looks like there's a circle. So once again, the circle I just drew is visible, right?
Yep.
Okay, and then it looks like, I don't know if these are true circles, but it looks like there's another circle over here. And another circle over here, symmetrically placed. It's supposed to be symmetrically placed. And then there's like a thing there. And a thing there. But they sort of continues, like this one continues to there. And this one continues out here to infinity. Okay, I think that's what it looks like. Now let me see if I can identify where the green vertexes are and the blue vertexes are. So I think it's something like, well, we did say that G was at 1, so, and G is supposed to be red. So I think there's a big red vertex right there. And by the red-green duality, the negative of a red vertex should be a green vertex. So I think it's like that.
Did you say that there are like 2 more secret vertices that?
Yes, and I said that they should be right there to get everything. Those that blue, yeah, that's blue.
Yeah.
This is where you put the, I don't know exactly where, but it says it's a freehand sketch anyway, but this is combinatorially correct. This picture is combinatorially correct.
Yeah.
And that's where you put the invisible vertexes in order to get everything to be triangles. Now everything is triangles.
Mm-hmm.
And I just have to figure out what everything else is. Well, all the triangles are supposed to be green, red, blue. So it looks like I must have, a green there and a red there. So I must have a blue right there. And, by the red-green duality, that must be another blue right there. And it looks like there must be a red there. So the triangles would be red, green, blue. And it looks like there must be a green right there. To be red, green, blue. Everything to be red, green, blue. So I think this is the way the vertexes look. And let me see if I can figure out which is which. I think it's something like this is B. So this must be A. No, A must be over there. G must be there. So this thing must be H over here. C, D, E, and F are a little bit harder to tell, but there's something like that. It must be, let's see, I think it must be, let's see, the invisible ones are C and F, so I don't know. And there is some freedom that allows me to switch here. So I think it's something like C and F there. And then it's really hard to decide where the D and E are. I'll guess that it's like D and E there or something like that.
Mm-hmm.
But if I manage to do this correctly, and then I connect it, and then I compare it against this chart, you should see that it actually works. So again, the propaganda message, the propaganda punchline is that a whole bunch of things are working to the point where, I have a very concrete understanding of what these Galois fields are and of what their corresponding Galois groups are in the Galois correspondence. And that should be very helpful in understanding the big picture, abstract Grothendieck-Teichmüller theory of what's going on here. And well, there is one more thing that I sort of want to tell you before we quit. Well, but it does depend on how much time you want to take. Do you want to quit at 4 p.m. or do you want to go another 10 minutes?
I'm getting sort of tired, unfortunately.
Okay. Then we'll quit here. But let me just think for a minute. So okay. I hope you can sort of see what's going on here. And the extra thing that I was going to do, but we'll have to postpone to next time, is I was going to try to respond to one of your sort of requests, or at least my interpretation of one of your requests, which was, one of the things that we're trying to do here is we're trying to understand Kronecker's Jugendtraum in the context of Grothendieck-Teichmüller theory.
Uh-huh.
And I sort of want to act that out for you with drawing pictures. I want to convince you that there's a very visual, naive, kindergartenish way to understand Kronecker's Jugendtraum. And so at some point, that's what I really want to try to do, but I won't try to do that right now. So
Okay.
there's probably all sorts of fun punchlines I'm forgetting, but I think we're just going to wrap it up for right now. Okay.
Okie doke. Yep.
Okay. So thanks a lot. This was very helpful. I'll talk to you later.
Okay, great. Yep.
Okay. Bye.
See you next time.